In last lecture, we have studied the basic principles of metallurgy and the first step in it, that is the concentration of ore. Today, we will see our next point, that is the second step, that is extraction of metals. Extraction of metals consists of three different types according to the reactivity of metals. First, we will see the first extraction method, that is the extraction of reactive metals. Some metals are more reactive, some are moderate, and some are less reactive. According to their reactivity, they have different types of extraction methods. First, we see extraction of reactive metals. The metals at the top of the reactivity series are highly reactive, and their reactivity decreases as we go down in the series. For example, potassium, sodium, and aluminum, these are the most reactive metals, and reactive metals have the large capacity to form cations by losing the electrons and in their outermost shell. For example, reactive metals react vigorously with the dilute acids to give hydrogen gas, and highly reactive metals burn by reacting with oxygen from air at room temperature. The extraction is done by the electrolysis reduction method, and the metals like sodium, calcium, and magnesium are obtained by electrolysis of their molten chloride salts. And in this process, metal is deposited on the cathode while the chlorine gas is liberated at the anode. That means the metal is deposited at cathode and non-metal is deposited at the anodes. And the electrode reaction during the electrolysis of the molten sodium chloride is given here as shown in the reactions on the page number 103. You can see the reaction at cathode and reaction at anode. At cathode there is a reduction type of reaction, and at anode there is the oxidation type of reaction. And in such a way, by electrolysis reduction method, you can extract the reactive metals from their molten states. Now we have to see the extraction of aluminum. You know that aluminum is the highly reactive metal, and we have to see how aluminum is extracted from its ores. Now we see the basic information about aluminum. The symbol of aluminum is Al. Its color is silver white, and atomic number of aluminum is 13, and according to atomic number, its electronic configuration is 2, 8, and 3, and valency is 3. Aluminum is a reactive metal and does not occur in the nature in free state. We know that the reactive metals are always in their carbonate or other compound forms. They are not found in nature in free state. Aluminum is the third highly abundant element in the earth crust after oxygen and silicon. The aluminum is extracted from its ore, that is the bauxite. Its formula is Al2O3 NH2O, and bauxite contains 30% to 70% of aluminum oxide, and the remaining part is the gangue. It is made up of sand, silica, and iron oxide, and there are two steps in the extraction of aluminum. First step is the concentration of bauxite ore, and second step is the electrolysis reduction of alumina. Now we see the first step, that is the concentration of bauxite ore. Bauxite is the main ore of the aluminum. Silica, ferric oxide, and titanium oxide are the impurities present in the bauxite. Separation of these impurities is done by leaching process and using either Bayer's method. That means for the concentration of bauxite we can use two methods, that is the leaching process, or by Bayer's method or Hall's method. In both the methods, finally the concentrated alumina is obtained by calcination. In the Bayer's process, first we see the Bayer's process. In Bayer's process, ore is first ground in a ball mill, and then it is leached by heating with concentrated solution of caustic soda at 140 to 150 degrees Celsius under high pressure for 2 to 8 hours in a digester. Aluminum oxide is being atmospheric in nature. It reacts with the aqueous solution of sodium hydroxide to form water-soluble sodium aluminate, and this means that bauxite is leached by sodium hydroxide solution. The reaction is given here. The iron oxide in the gangue does not dissolve in the aqueous sodium hydroxide. It is separated by the filtration, and however silica in the gangue dissolves in aqueous sodium hydroxide to form water-soluble sodium silicate. Aqueous sodium aluminate is diluted by putting in water and is cooled to 50 degrees Celsius, and this results in precipitation of aluminum hydroxide. The reaction is shown here. In the Hall's process, this is the Bayer's process. In Hall's process, the ore is powdered and then leached by heating with aqueous sodium carbonate in the digester. That means instead of aqueous sodium hydroxide, here sodium carbonate is used. Process is the same. in the diester to form water soluble sodium aluminate. Then the soluble impurities are filtered out and the filtrate is warmed and neutralized by passing carbon dioxide gas through it. This results in the precipitation of aluminium hydroxide. The reactions are shown on the next page. The precipitate of aluminum hydroxide obtained in both Bayer's and Hall's process is filtered, washed and dried and then calcined by heating at 100 degrees Celsius to obtain aluminum. And that means it is the first step to concentrate the bauxite ore. That is the first step, and next step is electrolytic reduction of the alumina. Electrolytic reduction, you know what this is the second step of the extraction of the metal. In electrolysis reduction of alumina, the apparatus used is shown in the figure number 8.12. In this method, electrolysis of molten mixture of alumina, we obtain alumina in the first step, that is the concentration of ore or concentration of metal. This alumina is used in the second step, that is electrolysis reduction of alumina. The molten mixture of alumina, whose melting point is above the 2000 degrees Celsius. This molten mixture is done in a steel tank. Here they have shown the steel tank. In this steel tank we have taken the molten mixture of alumina. The tank has a graphite lining on the inner side. You can see the black border on the inner side, that is the graphite border or graphite lining. This lining does the work of alpha cathode. This is the cathode. And set of graphite rods dipped in the molten electrolytes work as an anode. You can see the anode or graphite rods, they work as the anode. Cryolite and fluorspar. Cryolite, that is the Na3AlF6, and fluorspar, that is the CaF2. These two substances are used or added in the mixture to lower its melting point up to 1000 degrees Celsius. You know that the melting point of alumina, molten alumina, is above the 2000 degrees Celsius. We must reduce the melting point of this alumina, so we add these two substances, that is the cryolite and fluorspar, into the mixture, so that the melting point of the alumina, it will be lower up to the 1000 degrees Celsius. Then aluminum is deposited on the cathode. We know that at the cathode metal is deposited, and at the anode non-metal is deposited. From the alumina, aluminum is deposited at the cathode, and when we pass the electric current, this reaction is done, and molten aluminum being heavier than the electrolyte, it is collected at the bottom of the tank. Molten aluminum is heavier, so it is settled at the bottom, and it is taken out from there from time to time, and oxygen gas is liberated at the anode. You can see the outlet at the lower end of this steel tank. You can collect the aluminum from this outlet time to time, and oxygen gas, which is liberated during this reaction, it is collected at the anode, which is made up of graphite. Thus electrolytic reduction or reactions, electrolytic reduction is done here. The electrode reactions are shown here. At anode, oxidation reaction is done, and at cathode, reduction reaction is done, and the liberated oxygen reacts with the anodes to form carbon dioxide gas. You know that the anode are the graphite rods, and the liberated oxygen is deposited on the anode, and due to the reaction it forms the carbon dioxide gas. So the anodes have to be changed from time to time as they get oxidized during the electrolysis of aluminum. By this reaction the anodes are oxidized, so to remove this drawback we have to remove the anodes after time to time. So the working of these anodes must be done properly. Here today we have seen the second stage or second step of this basic principles of metallurgy, that is the extraction of metals. During the extraction of metals, different methods are used according to the reactivity of metals. Here we have studied the most reactive metal, that is the aluminum, how aluminum is extracted from its ore. The main ore used for extraction of aluminum is the bauxite, and in it two steps are there. First is the concentration of bauxite ore. For it we use the two methods, that is the Bayer's method or Hall's method or leaching process. After concentration of bauxite ore, we can use the second step, that is the electrolysis reduction of alumina. During the concentration, alumina is prepared in molten state. It is electrolysis or electrolytic reduction is done, and during this process the aluminum metal is extracted from the molten alumina. So you have to draw the diagram of this extraction of aluminum and write the short note on extraction of aluminum. Here we will stop today. Thank you.